Okay, I'm going to go through a few examples about how to use SPSS to analyze your data. This is the HSV modified data set. I have SPSS open. It looks a little bit different than the one that you'll be using, but all the menus are the same, and the file layout is the same as well. One thing you should do first is just check your variable view. If you look at the buttons down here, this shows me the data. If I click on the variable view, I get to see each variable, whether it's numeric or a string, and some other information about it. You should always look at this when you cut and paste data into SPSS to make sure that everything is numeric. A few people had a problem with that in the lab the other night, but not everyone, and I just don't want you to run up against it at home. But it shouldn't be a problem for what you're doing today. So I want to go through three things: the one sample t-test, the independent samples t-test, and the paired samples t-test. So let's look at reading scores right here. I want to know, first of all, if the reading scores of this sample that I have are different from the general population. And basically I want to know, say I started some new program and I want to see if these students are performing at or above what level they're supposed to be performing at. So I'm going to go to Analyze, Compute Means, One Sample T-Test. All I need to do is toss in my reading score. My test value in this case is the population mean, which I know, and I told you in the notes, is 50. So I plug that in, and that is it. I click OK, and I get my output. I have my sample size, 600, big sample, should find differences. This means I have a lot of power. The mean of my sample is 51.9, standard deviation is 10, standard error is 0.412. My t-stat is 4.61. This again means that the difference that I see between my mean and the population mean is 4.6 times what I expect it to be just by chance. We're not really talking about degrees of freedom. My p-value is below 0.05, so I know that I do have a significant difference in statistical terms. In other words, it's really, really unlikely that I would get a mean this high if in fact there was no difference between my sample and the population mean. It just won't happen. And that's it for the one sample t-test. Now the other thing that we wanted to check is whether or not, say, boys and girls differ in their reading ability. So I have my sex or gender variable here. I have my reading variable here. And what I want to do in this case, when I'm comparing two groups, is go to independent samples t-test. Click it. My test variable, again, is my reading score. And my grouping variable, which is going to separate different groups from one another and make comparisons, is my gender variable, and I first need to define them just by the numbers that they are. The reason that I need to do this is sometimes there are more than two values. So in other words, if I look at SES, there are 3 values here. If I looked at race, there might be 6, 7, 8, or 9 values, and so on. And I just want to identify which 2 I actually want to compare. I click OK. I get some more results. There we go. And if I look at my means, I see that the males in this group, and I have an unequal sample size, but it's not that big of a deal. I have males have a mean of 52.36, females have a mean of 51.52, and the question is this difference big enough to really be considered a true difference, or is it just something that's due to chance? I look at my first row here. Don't worry about this, we'll talk about this later. But I'm looking at my t-value of 1, meaning again that the difference that I see is pretty much the same as the difference that I would expect by chance. I see my mean difference is labeled right here, 0.846 point difference. My standard error is 0.828, so they are just about the same. I look at my p-value here, or my sig value. This means that the probability of me getting a t-stat this big or bigger given the standard error in my sample size and all that, happens roughly 31% of the time. And that is not enough evidence for me to conclude that there are differences. The last type of example I want to look at is the paired or related samples t-test. Now, typically I'm looking at changes over time, and if I look at my data, I have an initial reading score and I have a second reading score. And I want to know, do people systematically change over time? Or do people basically stay the same? And I can pretend that this is before and after they take my little brain supplement, or I could pretend it's before and after some kind of reading program and I just want to see if they're actually learning anything. So I can run a paired samples t-test. Now, I'm going to go to compare means, paired samples. When I'm putting my data in, let me just get it out of there for a second, I'm going to put in the second one first, because what the program does is it just kind of follows this equation, reading 2 minus reading 1, when it's looking at differences. And if there's an increase, in other words, if reading 2 scores are actually higher than reading 1 scores, this will be a positive number. If I put reading 1 scores in first, followed by reading 2 scores, I would end up getting a negative number, and that's not exactly what I want to do. It's going to misrepresent what I'm looking for. So I click OK. I look at my values here. I have a mean value for reading 2 of 52.04. I have a mean value for reading 1 scores of 51.9, and there's not a whole heck of a lot of difference there. I mean, if you're thinking about it, it's 0.14 points. So that's probably not going to really indicate anything. I look at my sample size at 600 of each, standard deviation of each, standard error of each, yada yada yada. The correlation is something we'll talk about at a different time. But if I look at my mean scores, I have a mean difference. In other words, on the average, people increased 0.14 points. Not a whole heck of a lot. I look at my standard error here, and it's 0.392. So typically, in other words, if I looked at the whole distribution of change scores or difference scores, whether it was plus half point minus negative 0.2 points, on the average, even though the mean difference was 0.140, if I pick somebody at random, they'd be about 0.4 points away from this actual mean, meaning that I have a much greater distribution. What I expect to see in terms of differences is a lot more than what I actually see. It's reflected in my t-ratio of 0.358, meaning that the difference I see is only roughly a third as big as what I would expect to see, just by chance, meaning that nothing's going on. In other words, my supplement doesn't work, or the reading program doesn't work, or nobody's learning a darn thing. If I look at my p-value here, it's 0.720. And again, what this means is that the probability of getting a t-value this big or bigger, if the null hypothesis is true, is 0.72. In other words, I will get a t-value of this magnitude, whether it's positive 0.358 or negative 0.358 or greater, 72% of the time.